Thank you for the very kind introduction. Yes, so as mentioned, I'll be talking about how to succeed when working with Schlenk lines. Um, we went through the kind of outline of the presentation today, and there'll be plenty of time towards the end to answer any questions that you have, any specific ones about equipment or techniques or troubleshooting that seem quite common. So, as many of you know, there's lots of elements, reagents, materials that are sensitive towards air and moisture that are in the atmosphere. And whilst many non-chemists might believe that this hinders their practical applications, it often means they have really high reactivity, they have unique properties. So we want to utilize them, and we need methods to be able to do so safely. So as a classic example in industry, organometallic reagents are used on a day-to-day basis, such as organolithium compounds. They're used for a range of stoichiometric transformations in the pharmaceutical industry, or even in material science towards polymerization reactions. And of course, in research laboratories, we're using air and moisture sensitive compounds on a daily basis. It's not just limited to synthesis. And if we want to handle them safely, both to use them in an application or to make new compounds that happen to be air and moisture sensitive, then we of course need specialized techniques, which is where Schlenk lines come into play. Now, Schlenk lines are derived from Wilhelm Schlenk, a pioneer of organolithium chemistry. And even though many other chemists were using inert atmospheres prior to 1913, it was in this publication that he started to document and illustrate what kind of equipment is needed to be able to perform these on a routine basis. And this is, of course, how Schlenk lines that we know and love today were developed. So this is an illustration of a typical Schlenk line. And what we have are a dual manifold system. One of the manifolds, of course, holds our inert gas, and this is fed by a inert gas inlet and regulator. So the inert gas inlet and regulator allows us to monitor and control the inert gas flow rate as well as the pressure. And we obviously need a way for that to safely exit the Schlenk line, and this is through a bubbler, which is something I'll talk about towards the end of the presentation. We also have a vacuum manifold, which is kind of controlled by our vacuum pump. Again, I'll talk about these later on. And in between the pump and the Schlenk line itself, we have a cryogenic trap. So this is most commonly a dewar of liquid nitrogen, although you can use other cryogens such as dry ice. And this condenses any volatiles or solvents that we remove under vacuum so that we collect them and, of course, protect our pump. Most Schlenk lines may have a manometer which is directly attached to the vacuum manifold. This allows the vacuum pressure to be measured, so we're always aware of how good that vacuum is, and that is really important for making sure that we have no leaks and, of course, have the best possible vacuum. Another feature that is common but not always included in Schlenk lines is what we call a vent valve, so this yellow valve here. This can be a PTFE piston or a kind of stopcock, and this allows us to safely repressurize the Schlenk line at the end of operation. We also have flexible hosing. This can be made from rubber or a thermoplastic, and this is flexible enough that we can connect different size flasks at different positions which are needed for a range of different applications. And the control aspect of Schlenk lines is essentially the double oblique stopcocks as shown here. So when they're in this side-on position, which is depicted here, we call that the closed position. And if we look at a side-on view of kind of the dual manifold system and the double oblique stopcock, the double oblique refers to the two holes that pass through the key, and in this side-on position, that there's no kind of through channel from either the vacuum or inert gas manifold to our outlet, which is the hosing. However, if we have it in this upright position, which is denoted with the blue in the upright position, we can see that we now have a continuous channel for the vacuum, and when we turn it 180 degrees, we now have the inert gas. So these color coding systems aren't built into your Schlenk line, so I highly recommend that you color code your taps either with some electrical tape or a permanent marker, and you can see you can also have the same markings on your vacuum manifold and inert gas manifold yourself, so you always know which is which. It doesn't have to be two colors, you can simply mark just one so that you always know without having to look at side-on view. An alternative to double oblique stopcocks are Teflon taps or pistons. And these have to be controlled independently. So you have one for inert gas and one for vacuum. Again, they can be color coded if you want. And these simply screw open and screw closed. And when they're closed, the Teflon is partially malleable. It will form a perfect seal with the glass. And when it's open, of course, the air or the inert gas can flow right into your system. Now, the benefits of the Teflon taps is that you have much finer control of your vacuum and inert gas. They're completely greaseless, so you avoid any contamination. But there is, of course, a risk that you can accidentally have both inert gas and vacuum open at the same time, which has many risks because you can then potentially condense your inert gas. You're, of course, wasting your gas. And on the contrary, when we have double oblique stopcocks, it's only possible to have either inert gas or vacuum open at one time. So this is perfect for training purposes. It's much quicker. It's better for people who might have dexterity issues. So you might come across both of these in your laboratory, and over time, you'll have a preference of which one you like and which ones you dislike. Now, the first thing that we do when we have a Schlenk line is that we have to assemble it to some degree and turn it on at the start of operation. And what we first want to do is ensure that all of these stopcocks are closed. If we have something that is connected to the Schlenk line, such as the reaction that was running overnight, then it might have to be under inert gas, but that's completely fine as long as none of these are open towards the vacuum. We want to attach a clean and dry cryogenic trap to the Schlenk line. Many of these have ground glass joints, so if necessary, you may need to apply a bit more vacuum grease on the male joint, and you attach it and twist it into place so you have a streak-free coating, and then preferably you attach a ket clip to secure the cryogenic trap in place, because when it's on without the vacuum, it can still, of course, fall under gravity. I should just note that some of these cryogenic traps might be greaseless, so just keep that in mind that every Schlenk line and all the equipment may look different to the illustrations you're seeing today. We also want to ensure that the vent valve is closed, and by this point, all of the kind of openings are closed on your Schlenk line, and that allows us to then turn on the vacuum pump. And preferably, you'll allow the pump to run for 5 to 15 minutes to kind of warm up, and also to evacuate your Schlenk line and any kind of residual parts. If you do have a manometer attached to your Schlenk line and you have a well-performing rotary vane pump, for example, you typically notice that the vacuum pressure at this stage should reach around 1 times 10 to the minus 2 millibar. And when you submerge the durate in liquid nitrogen, you may see that go down an order of magnitude because you've then, of course, are slowing down any residual gas molecules that are within your system. And if you did leave it for longer, it would, of course, go down, but that is definitely sufficient by that point. You just don't want to add the cryogenic trap too early on before you had a chance for the system to be evacuated. When you're turning off the Schlenk line at the end of your day, then we do many of the steps in a similar backwards order. Again, you want to make sure that the stopcocks are closed or turn to inert gas if we're leaving a reaction to run overnight. We turn off the vacuum pump, remove the duo of liquid nitrogen, and then open the vent valve to repressurize the vacuum manifold. Now, these are done often in quick succession, so the exact order doesn't matter too much. It's just important that you never open the vent valve when both the pump and the liquid nitrogen duo are there, because we run the risk of liquid oxygen contamination. What you may find on many Schlenk lines is that there's an additional tap or a stopcock between the vacuum pump and the start of the Schlenk line itself, and that allows us to isolate the pump completely from the line, so we can often close that before we do the next steps, as mentioned there. We want to, ideally, if you've collected some solvent, it's good practice to turn off your Schlenk line around 30 minutes or so before you're leaving for the day, and this allows the solvent that is collected in the cryogenic trap to warm up to room temperature. This means that this itself will be warm enough to handle. If it's too cold, it's obviously risk of cryogenic burns, and it means that the grease is quite tacky, so it's hard to even release if it's in place. And we can, of course, then discard of any collected solvents in an appropriate waste container, rinse this out with acetone if necessary, and allow it to air dry overnight so that when we come to do our chemistry the following morning, it's, of course, ready for operation. Whereas if you leave it overnight, you have to kind of do that all in the morning, and you run the risk that collected solvents here, if you don't have an additional tap to isolate the pump, can still evaporate into your pump oil. Now, the glassware that we use when we're handling air and moisture sensitive compounds, of course, needs to be free of water, and we do this by storing them in ovens that are typically above 100 degrees. Ideally, this is done overnight, but even a few hours prior to use should be sufficient to kind of get them ready, especially when we need to put them under vacuum. So these are the typical components of a Schlenk line. This is a Schlenk flask, sorry. This is a round bottom styled flask where we have the flask itself, which is has the stir bar in from the beginning, a stopcock and a stopper. This is a single oblique stopcock with a single straight hole. And we assemble these by first greasing the stopcock and the stopper, inserting them into their corresponding joints and twisting to ensure we have a streak-free coating. If you see that there's some resistance or that it's kind of patchy, then you might need to apply more vacuum grease. Just keep in mind that it's easier to add more grease if necessary versus to remove a lot more and run the risk of contaminating your flasks. And once your flask is assembled and connected to the Schlenk line hosing, we place that under vacuum. Now, if you've done that fairly quickly after removing the glassware from the oven, then of course it will stay hot for quite some time. So the first cycle may be between 5 and 10 minutes. But if it's a smaller flask that cools down quickly and obviously have less volume, then even several minutes for the first vacuum should be sufficient. And once we've done that, we want to backfill it with inert gas. And we refer to this as a cycle, so you might hear the term cycling onto the Schlenk line, and we repeat that 3 times to remove all air and moisture. So if you imagine that one cycle gets rid of 90% of the air and moisture, then by the time we've come to 3 cycles, we've gone to 90 to 99% to 99.9%, akin to how you use multiple extractions in a kind of organic aqueous washing step in a workup. So keep that in mind, that one long cycle is not going to be better than 3 shorter cycles. So with that in mind, it leads on quite nicely to the working principles of Schlenk line chemistry. And these are really important to keep in mind, so you're always aware of the steps and stages you should be doing. So as I mentioned, we perform these vacuum inert gas cycles to remove air and moisture from oven dry glassware, even to evacuate the hosing, or when we want to attach a solvent ampule to the Schlenk line, we have to perform these cycles. When we do have inert gas flow, then we want a slight positive pressure. This means that when we're replacing stopcocks and doing some other operations, if there's ever a leak, then we have a positive flow of inert gas that is coming out of the flask, which makes it very difficult for atmospheric air or moisture to get in. And this is especially true if we work with a denser inert gas such as argon. We use dynamic vacuum to remove volatiles, so we can use the pump that's directly on the line to remove solvent under vacuum. Because of the power of an RV pump that is typically attached, then we can remove fairly high boiling solvents at atmospheric under ambient temperatures, for example, whereas when we use, let's say, a rotary evaporator, then you often have some gentle heating and less of a vacuum to remove your solvent. But of course, by doing all of this on the Schlenk line, we never expose our reaction media to air or moisture. We use greased ground glass joints or Teflon taps kind of for all our connections, but especially so when applying vacuum. So you want to avoid having a rubber scepter or even different kinds of Teflon taps that aren't kind of greased when applying vacuum, because they don't form permanent seals. So that's something to keep in mind. And the only time we do want to use rubber scepter is when we're manipulating liquids under an inert atmosphere. And this is especially true when we perform a cannula transfer, which is the first key technique that I want to talk to you about today. And the way that these work is that it relies on a differential inert gas pressure to transfer liquids between two sealed flasks. And by sealed, I mean that they're both under inert gas in a controlled way. So the first thing that we need to do is we need to replace, if we have ground glass stoppers or Teflon taps, with suitably sized rubber septa, again under a positive flow of inert gas. And we want to be able to purge the cannula because a cannula can't be evacuated because it's a double-ended straw essentially. Then the next best thing is to purge it, and this is the process of passing inert gas through it for 15 to 30 seconds to remove the air, and we can also store these in an oven so that removes obviously any adsorbed water, and then we can insert it into the corresponding receiving flask. So as shown here, a common time that we're going to use a cannula transfer is to dissolve a solid in an anhydrous solvent. So this is a solvent ampule and this is our solvent. And to initiate the transfer, we need to lower the cannula down into the solvent level, close the stopcock, and then insert a bleed needle. So a bleed needle, or sometimes called an exit needle, is just a clean, dry needle that allows the gas to escape. And as depicted by these purple arrows, you can see the flow of inert gas. It comes in through the flask, it pushes down on the liquid level, which pushes it along through the cannula. And because we have this here, the inert gas then exits the flask. If we didn't have this, then there's nowhere for the gas to go. And because we have a bubbler, you're never going to get gas buildup, but there's no preferential pressure. And once we've added desired quantity of liquid, then we remove this above, pull it above the liquid level, open the stopcock and remove the bleed needle. Now, the cannula transfers are great if you need to do bulk transfers, if you're not too bothered about the exact volume, but when you do need precise volumes, then this is where we start to use syringes and needles, and it also means that we're often working with shore seal bottles or reagent bottles that have rubber septa built into them. So one thing that's important when we're using these shore seal bottles is that we need to have an inert gas inlet to re-equalize the pressure. If we simply put a needle through the septa, withdrew the amount of liquid, and then pulled that out, then that would be under a partial vacuum. And because we've now compromised the seal, air would want to find its way into that bottle. So we need an inert gas inlet at all times. And what I really recommend that people use when doing this are these so-called Lure Lock needle to tubing adapters. So this barbed end goes into the hosing, which we can further secure with a hose clamp. And then this section here, the needle actually twists and locks into place. And this is much safer than some of the kind of cut a syringe in half and put some tape around it. So if you're going to be using these on a routine basis, then these are a really good investment. You want to ensure that the reagent bottle and of course your tubing is secured in place with hosing so that they don't accidentally come out. And the first step of this is that we need to purge the syringe. So similarly to cannula, we can't evacuate the syringe, so we purge it. We do that by inserting it into the headspace of the reagent bottle. You can also do this into the flask that you're going to be adding it to. That ensures that this rubber septa stays quite in good condition. Once the syringe is purged, we want to withdraw the amount of liquid that we need, plus some extra. And the reason for getting that extra amount is that we need to also remove the gas bubble that inherently comes over. One thing to mention when we're withdrawing the liquid is that if you ever see that the liquid seems to be bubbling inside, then that suggests that you're pulling the plunger too quickly, so that the inert gas inlet can't kind of keep up with the rate that you're going. So if you're doing that, you're essentially creating a partial vacuum, so that should be avoided. We remove that gas bubble by turning the syringe vertically. So for a lot of these applications with sure seal bottles, you may use these 10 centimeter or so disposable needles that are flexible. And then we can depress the plunger to remove the gas bubble and get down to our desired volume of liquid that we want to transfer. And this can be removed and then added to our reaction vessel. Something to note is that, as shown here, this is transferring N-butyl lithium. You're probably going to be using pyrophoric compounds. One way that you can kind of facilitate the transfer without risk of a spark is you can, once you've got the desired volume of liquid, withdraw a kind of cushion of inert gas. I personally find that you need to keep the syringe in the same position during the transfer so that it doesn't come out. But you can, it's also not super critical that you do so. It's personal preference, I would add. So going back to our cannula transfers, a kind of another key technique is the cannula filtration. And we use this when we want to collect crystalline material, or if we want to remove a solid or precipitate that settles quite nicely to the bottom of the flask, or it's coarse enough that we're not going to run the risk of clogging our cannula filter. Again, this relies on the same principle, but these cannula filters you often construct yourself. You can get similar things that you can buy in a tub and you can simply stick to the end of an appropriately sized cannula. So shown in the picture is a kind of microfiber filter, but you can also just use a simple bigger filter and cut them into squares. This is a PTFE cannula and 2 strips of PTFE tape, usually cut between 10 and 15 centimeters in length. You wrap one length around it first, and then you add the filter paper and fold it in such a manner that you can secure it in place with the second strip of PTFE tape, whilst leaving that end kind of very flush and not wrapped in PTFE tape. This is obviously too thick to go directly for a rubber septa, so you need to insert it through the underside of the septa first and pull it along when we first replace the glass stoppers or Teflon taps with the rubber septa. Again, the filtration process happens in the same way as a cannula transfer. You may have greater resistance, so you might need higher inert gas pressures, and to prevent blocking of the cannula, it's recommended that you lower this slowly down into the liquid level before shoving it straight down into the bed of your solid. And it's always worth having some of these pre-prepared in ovens prior to use, because if you need a backup, then one is always ready and dry when you need it. On a kind of different topic, another key technique that I want to quickly talk about is the freeze pump Thaw method, and we use this to degas solvents or other liquid reagents. The first thing that we want to do is add our liquid to a suitable Schlenk flask or an ampule, and we seal it under ambient pressure. So that can be under inert gas or air, depending on the application that we need. And then we carefully freeze it in a jar of liquid nitrogen. We want to do this slowly. Keep in mind that some liquids might expand when frozen, so if you keep it moving when you're first doing the freezing process, that can help with that. And you want to ensure that the liquid is fully frozen. So that might take a while depending on the liquid, or especially the volume of liquid that you're trying to freeze. And once it is, then we can evacuate the headspace by opening the stopcock to dynamic vacuum. Because we rely on the headspace, it's worth noting that you don't want to fill the flask too much, so no more than 2/3 full, ideally half full should be sufficient. And once we've evacuated the headspace for several minutes, we seal the flask and we allow the contents to slowly thaw and warm up to room temperature. During this process, any dissolved gases that are in the liquid will be pulled from the liquid into the headspace, and we'll repeat this process 2 more times to kind of, again, get rid of all of the trapped gas. You do want to avoid applying external heat when doing the thawing process. Of course, even going from liquid nitrogen temperatures to room temperature is already a 200-degree jump, so any further heating can cause tremendous strain on the glass. So be patient and allow plenty of time when doing the freeze pump Thaw method. Once we are satisfied that we've degassed it, we can then backfill it with inert gas if our plan is to just store it long term under an inert atmosphere. But you can also use this process to backfill with a reactive gas such as dihydrogen, carbon monoxide, carbon dioxide, and so on. Now, the freeze pump 4 method is quite dangerous, so don't do this without direct training. And the reason it can be extremely dangerous is that you never want to backfill a flask with inert gas whilst your flask is frozen in liquid nitrogen. And the reason for this is that you can obviously condense nitrogen and argon at these temperatures. And this alone isn't the biggest problem in the world, but if we accidentally close this, then as it warms up, that gas will expand and you have a really high risk of explosion unless we're using glassware that is rated for higher pressures. I want to talk about briefly the types of distillation that can be performed using a Schlenk line. For many organometallic, inorganic main group chemists, half of our job seems to be drying and purifying a lot of the reagents before use, so we're very familiar with the types of distillation that can be performed. So the first is what we call a simple distillation. We use this for very routine purification and drying of solvents and liquid reagents when their boiling points is typically below 150 degrees. You can go slightly higher and you can use just an oil bath or a heating mantle to do so. And shown in this picture here, we have kind of like a one-piece construction, which has a Vigro column built in, and then we have an external cooling jacket with water, a thermometer, and a receiving flask, which is in ice if needed, and we can either have the inert gas coming in through this vacuum takeoff adapter or through the Schlenk line, a Schlenk flask that we have attached also. Here, even though I'm holding it, this is actually closed so that we don't ever run the risk of this solvent evaporating through this way. It always have to go from hot to cold and be collected here. Another type of distillation is what we call a dynamic vacuum distillation. We use this for the purification of high boiling liquids and oils, and you can even use this for low melting solids. Now, the difference here is that, again, we want a distillation bridge that has as few parts and joints as possible to maximize the quality of our vacuum. And because we do often need a higher external heating to the kind of crude reaction mixture, you generally don't need like an external cooling of the bridge itself. Even air is sufficient to cool it down, although you can still cool your receiving flask in a suitable bath to prevent any further evaporation. And after the distillation is done, we allow both flasks to come up or down to room temperature, and then it can be slowly backfilled with inert gas and reassembled so that we can do further storage or reactions with our purified liquid. The final main type of distillation is what we call a static vacuum distillation, also referred to as a vacuum transfer. And again, this is used for the purification and drying of fairly low boiling liquids and solvents, whilst trying to minimize evaporative loss. So by that, I mean that we don't have any left behind. We don't have any risk that it's being evaporated up into tubes because we're working with a completely sealed system. So you'll see that this is often used for the purification of deuterated solvents or kind of fairly expensive reagents. And whilst I don't have time to talk about this in detail today, you'll see all the kind of step-by-step guides in both the Schlenk Line Survival Guide website and also my organometallics tutorial. Now, it's very important that we talk about the safety considerations and the dangers when we're working with both vacuum and pressurized inert gas systems. The main one when we're working with Schlenk lines is the condensation of liquid oxygen. And this will happen or has a risk of happening anytime we're using liquid nitrogen cooling traps. And if there's a leak or if we accidentally open a tap to vacuum, which is open to air, then we can get liquid oxygen condensation, which is characterized by a light blue color. And liquid oxygen alone isn't dangerous, but when it's combined with organic solvents that may be collected in your flask or even grease, has the risk of being very dangerous. So be aware of that at all times. It may mean that you consider using other cryogens to completely mitigate the risk of liquid oxygen. As mentioned earlier, we have an explosion risk. So we have the potential for buildup in pressure within closed systems. So this can be through heating, either when we heat a reaction up, or if it's a thermal runaway, or if we're going from cryogenic to ambient temperature, as I mentioned with the freeze pump Thaw method, or of course if a reaction generates gas. So if you're using N-butyl lithium for a deprotonation, you're going to generate butane. So you need to make sure your flask is open so that that gas can safely escape. On the flip side, there's a implosion risk. So this may occur if we attach a Schlenk flask under vacuum and there's a damage to it. So this may be in the form of a hairline crack if it's scratched. So always inspect your glassware prior to use and never put something that's damaged under vacuum. As mentioned a few times, we are very frequently handling pyrophoric substances. So we need to safely quench these prior to disposal and cleaning, but we also need to have appropriate fire safety measures in place. So that'll include a fire blanket, sand, an extinguisher. Sometimes you may want supervision from a more senior member of the group. You want to make sure your fume hood is clear of any solvent bottles, and of course a risk assessment prior to handling if necessary. And there's lots of other hazards, such as the frequent use of sharps through needles, steel cannulae, using and adjusting gas cylinders, and cryogenic burns from handling dry ice and liquid nitrogen. Now, kind of one of the most frustrating aspects of Schlenk line chemistry is the fairly regular troubleshooting that goes on with it. And when we want to troubleshoot our line, it means that we need to know our Schlenk line. And what I mean by this is that we know the usual vacuum pressure. So if we have a manometer built into our system, then we obviously know exactly what our vacuum pressure is every day. But you can also get a hint how good your vacuum is without a manometer by how easily certain solvents are removed under vacuum. So if you ever see a deviation from this, then there's a problem that needs to be addressed. The typical inert gas flow rate and pressure. So this is where the bubbler comes into play. So knowing that is really important. And even simple things like what your vacuum pump sounds like. If it sounds different, it might be working harder because there's a leak or there's some contamination. And I really want to emphasize that you do often have to use all your sensors to detect the problems, and it's important that we routinely check and test your equipment. Now, the most common problems that people encounter when working with Schlenk lines is, of course, poor vacuum pressure. And this inherently suggests there's a leak somewhere within the Schlenk line. And whilst you may think my vacuum isn't great today, that's not a big problem. It should be addressed immediately because you can lead to oxygen condensation if you are using liquid nitrogen cooling traps. As I mentioned, if you have a manometer, it's easy to see, or as I mentioned, you might just see that some solvents are difficult to remove under vacuum. And if possible, the best way to identify the problem is to isolate and test individual parts of your Schlenk line, and that helps you to locate the source. And 9 times out of 10, if you have double oblique stopcocks, you'll find that some of the taps are just poorly greased. They do kind of start to seize and get worn away over time, so you may need to re-grease some of those taps. Or you may have damaged or loose Teflon taps if you have a completely grease-free line. The two other main reasons why you might have poor vacuum pressure is that you have a blockage in the solvent trap, and this often happens if you're trying to evaporate a solvent such as benzene or 1,4-dioxane, which freeze at around 0 degrees Celsius. So that means that even with a liquid nitrogen cooling trap, towards the top of the trap, it might be around 0 degrees. So it might collect towards the top in the kind of inner tube before it has a chance to fully collect at the bottom of the solvent trap. One way that we can mitigate this is by using an external solvent trap, and this is also true if we want to ever remove large quantities of solvent. I would recommend that you never remove more than 50 mils of solvent directly on your line. It's always much better to use an external cooling trap. And bear in mind that when you are, even throughout the day, and especially when removing solvent under vacuum, your liquid nitrogen will start to evaporate, so that has to be topped up during the day. And if after all of these attempts at locating the source, you still see poor vacuum pressure, it might suggest there's a problem with the pump. So do remember to frequently ballast your pump and change the oil regularly if you are working with rotary vane pumps. The kind of second main problem that you may encounter is that your cannula transfers and especially filtrations are slow. Again, this deals now with the inert gas side of things, so you may still have a leak to some degree. So the septa that you're using may have some leaks. A stopper may have popped off without you noticing. So if the inert gas has somewhere else to escape through, then that would stop it. And if you have a blockage where the inert gas can't safely escape, then that would also stop or slow down the filtration. If the cannula transfer or filtration fails to initiate, then you often need a greater pressure differential to begin with. So that can be done by often slightly blocking off your bubbler if you have an oil or mercury bubbler, or if you have an overpressure bubbler to simply increase the pressure there. One thing that we can often do when doing these transfers is to manipulate the height of the flask. So we can raise the height of the transfer flask and lower the height of the receiving flask so that once the transfer happens, you have a kind of inbuilt siphon that kind of keeps it fairly continuous. Kind of on the note of bubblers, I do want to talk about kind of the options that you have. As I mentioned early on, they have lots of different uses. The first is that you can see the inert gas flow rate, so you can monitor that, and it also provides a safe pressure release system within the Schlenk line so that you never have a buildup of an inert gas. They also act as a one-way valve, so inert gas can escape, but atmospheric air and moisture can't come in to come and contaminate your reactions. So the three main types include the oil bubbler. So these are the cheapest and most common that you'll see in most laboratories. The kind of downsides to these is that the oil itself doesn't have much viscosity or density, so you don't have as high of an inert gas pressure. You can make the flow rate as fast as possible, but it might not impact the pressure that you're reaching in your line. Another problem that you may encounter with oil bubblers is the risk of suckback. So this is if you pull a vacuum here, you'll get oil in your line potentially and contaminate it, and then it'll be a real challenge to clean. The second option is an overpressure bubbler. So these still contain oil, they have this valve, and they have a spring that applies pressure to the valve so that only when a certain pressure is reached does the bubbler bubble. And you can change the pressure by twisting this, and also so these are really fantastic. The main downsides to these are that they are fairly expensive. They do get some getting used to when you're working with higher gas pressures for the first time. So you may need to have spring-loaded fork clamps to kind of make sure everything is safely in place. One thing to note that people often don't realize is that you might actually save money on inert gas when using these because you don't have a continuous flow of inert gas, and that also might limit how much exposure your reaction media actually gets to the trace air and moisture that is within your gas. The final kind of bubblers are mercury bubblers, so they work on the same principle to oil bubblers, but we're now dealing with a very high density liquid metal that provides a lot of resistance. And you'll also note that mercury bubblers are often really tall, sometimes even a meter, and the reason for that is that by definition, 1 atmosphere can support 760 millimeters of mercury. That means that even if we apply a vacuum to the bubbler and to the inert gas manifold, that will only stay at 76 millimeters, so that we can evacuate the inert gas manifold. That's particularly useful if we first assemble in the Schlenk line, we're cleaning it, if we want to flush out a reactive gas that we've put through it. But of course, they do come with the obvious safety concerns of dealing with large amounts of liquid mercury. The other piece of equipment that, of course, I want to talk to you about is vacuum pumps. I've mentioned various aspects of these throughout the presentation today. And most Schlenk lines are equipped with rotary vane pumps. And a good rotary vane pump will get down to 1 × 10⁻³ millibar. They're suitable for Schlenk line chemistry because they have excellent vapor handling capability. The problem with this comment is that people often neglect the health of their vacuum pumps. So you really do need to keep in mind that oil changes should be every 6 to 12 months, depending on the usage and possible contamination, and also gas ballasting. So ballasting is essentially almost degassing the oil, so we can remove any gas or volatiles from the oil. So if you're ever working with large quantities of pentane, ether, dichloromethane, or low boiling solvents, then it's very beneficial to ballast your pump at the end of the day or the start of your day to ensure that it is operating as good as possible for your next applications. Now, something that's fairly new on the scene when it comes to vacuum pumps and especially Schlenk line chemistry is VacuBrand's VacuPure 10C screw pump. Now, what's amazing about these is that they're 100% oil-free while still being chemical resistant and having no wearing parts. And they can still achieve working pressures down to 5 × 10⁻³ millibar, so in the same range that we expect from rotary vane pumps and that we need on a day-to-day basis for Schlenk line chemistry. Again, they have excellent handling of aggressive gases and vapors. The main kind of benefit is that we can even operate these without the need for a cold trap. So this can, again, save you lots of money in the long term because you're not having to use liquid nitrogen on a day-to-day basis. And of course, because we're not using any oil, we don't need any gas ballasting, we don't need any oil changes, and none of that other routine maintenance that we expect for a rotary vane pump. If you are using this with a cold trap, they have an integrated regeneration mode. So this is a process that allows the inside of the pump to be cleaned. And the interface is really simple. So it has a pause, play, and stop button. And if you consider an RV pump as an analog version, then this is definitely the digital version. It even has lights that blink at different rates to tell you what a certain problem is, so it's very easy to troubleshoot. So if you want to learn more about the VacuPure, especially for Schlenk line applications, then do read the blog post that we put together for that. Another fantastic bit of equipment, particularly from VacuBrand, is the VacuSelect and VacuView extenders. So these are the vacuum controller and gauges shown in the picture here. And what these allow together is the precise control and measurement of pressures all the way from atmospheric pressure down to fine vacuum. So even down to 1 × 10⁻³ millibar, which you see in both of the displays. So the manometer shown here, the VacuView extended, has a very easy readout. And then we have this touchscreen monitor and control for the vacuum select gauge, which allows us to kind of have predefined programs for routine applications and customization. So you can have different programs for removing certain solvents. You can limit the ultimate vacuum that you have within your system, which is potentially good for some training applications. And you can really plug and play these, and these are all controlled by this solenoid valve shown here. And what I really found quite useful for these is that you have really controlled and also extremely reproducible distillations and sublimations. So you may find when you're doing a vacuum distillation or sublimation that you kind of only have control over one of the two factors, either the vacuum or the temperature. It's very hard to control both independently. And that means that when you want to do the same distillation or sublimation in the future, or someone else wants to repeat it, you'll often find that it's a much different temperature or vacuum because you have different pieces of equipment. Whereas, as shown here in these examples, you can have very reproducible distillations because you set a mild temperature and a mild vacuum. And this is especially important if you're distilling large quantities of something expensive and you want to ensure that this is done as safely and quickly as possible. Kind of an aspect of the Schlenk line equipment that I want to talk about is vacuum grease. I've mentioned it in a few different stages. We use this because it's a low volatility lubricant, so we need to have uniform and airtight seals between our ground glass joints. And there's three main kinds that you will encounter in your day-to-day laboratory. Silicone grease is cheap and widely available, good operating temperature range. The main downside being that it has limited chemical resistance, so it's easily activated. The silicon oxygen bonds can be cleaved, and it's prone to something called creep, which is when the liquid component kind of starts to seep out of certain joints, and that means that it readily contaminates reactions. So everyone, and probably 90% of NMR spectra that exist from publications contain some grease because it is so difficult to remove and avoid contamination. That's not to say it's not great. It's still suitable for day-to-day applications, but not permanent joints. And what I mean by that is I wouldn't use this easy for double oblique stopcocks, but for Schlenk flasks for the cold trap, then this is great, especially because it's so cheap. The kind of next step up is hydrocarbon grease. Again, as you expect, this is much more expensive than silicone grease. It has high creep resistance. It's still possible to contaminate reactions because it is soluble in especially aromatic hydrocarbon solvents. But it does mean, and the same is true for silicone grease, that if it's soluble, it's easy to clean at the end of operation. And there's, as seen in the picture here, for one particular brand, there's numerous different types available. Some are low temperature specific, some are high temperature, some are more for long-lasting permanent joints that you don't want to seize. So always keep in mind that for certain applications. But this is what I would use for double oblique stopcocks. The final type of grease is PTFE or PFPE grease. Again, more expensive than silicone grease. This is made from Teflon essentially, so it's chemically inert. It's practically insoluble in most solvents. So whilst you get the benefit of not contaminating reactions, especially through a distillation, it's difficult to clean joints when we need to once we're done with our glassware. It is still prone to creep, and it's also fairly prone to seizing, so you might even see that it splits quite easily, the liquid and solid components. So again, don't use these for permanent joints. I've shown a lot of illustrations, so I just want to very quickly show some pictures of some routine equipment. In this shown here are some Schlenk flasks. This on the left side is a male flask, so these are really useful if we want to dry some solids under vacuum before putting it into a glove box. It means that the grease will never come in contact with the solid here. And instead of a stopper, we have this Schlenk cap, often called a Viking helmet, if it has these spikes attached. So these are really valuable to have in your arsenal, and a few different kinds of Schlenk flasks that come in different sizes. Some have both ground glass joints and Teflon taps. These are particularly useful for distillations. These solvent ampules are really good for the storage of liquid reagents and hydrosolvents, and the smaller sizes are really good for kind of small scale reactions also. Rubber septa come in different sizes and shapes depending on the size of your flask. We have different clips to secure our stoppers into place. Cat clips and metal clips may be sufficient for most applications, but these spring-loaded fork clamps are really, really great, particularly when you're working with higher pressures within an overpressure bubbler. Here we have a range of different syringes. So the top is a vacuum tight glass syringe, so these are non-disposable, so these are good when you're transferring precise volumes of solvents. This is a 6 milliliter disposable syringe, and you can also get microliter syringes from 5 to 250 microliters. Again, if you need a small scale reaction or just kind of a catalytic amount of something. Cannulas, the two main type of PTFE, which are shown earlier, but it's also common to have stainless steel. The benefit of the stainless steel is that they have much sharper ends. So if you're ever trying to transfer directly out of a SureSeal or AcrySeal reagent bottle, then you'll need the sharper, firmer end to penetrate that seal. Whereas for the Teflon PTFE ones, it's hard to get a sharp point, but you can obviously see when it is contaminated or blocked, and then you can dispose of it if that is the case. There's a range of different needles. This top one is kind of a long stainless steel one, which again, coupled with this glass syringe is perfect for solvents. This kind of 10 centimeter disposable one, which most people will use for most reagents, particularly for the SureSeal bottles, and a smaller one which can be used as a lead needle. So that already brings me to the end of my presentation today. I'd only had a chance to talk about a few of the key techniques. So if you want kind of step-by-step illustrated guides for routine and advanced techniques and even some common synthetic procedures, then please go to the Schlenk Line Survival Guide to read more about that. There's also questions and pages about cleaning, assembly of Schlenk lines, a lot more detail and links to equipment. So do look at that. And the other resource that is available is my peer-reviewed tutorial published in Organometallics. This has been peer-reviewed by experts in synthetic chemistry, so you can be sure that the guidance you get in here is kind of respected. It's 14 pages, so it's suitable to be printed, so it helps being a perfect training resource for either undergraduate or research labs. And something that was done a bit more recently is that this organometallics tutorial has been translated into German, French, and Spanish, so hopefully that expands the reach of this tutorial. So with that, I'd like to thank you all for your kind attention. I saw a few questions coming in during the presentation, so I'd be very happy to now answer those for you.
Thank you for the fantastic presentation. We have indeed a few questions, and please don't worry, we will submit a link to the Schlenk Line survival guide and like to the blog post after the webinar to all the registered people. We've also done a recording, so like for everybody who missed the webinar from your colleagues, maybe you can happily share the recording afterwards. But now let's come to the questions. So first one is there a preference between flame-dried or oven-dried glassware?
Personally, I prefer the oven dried just because we know it's ready. So that's the main benefit is that it's ready. It's in there for a longer period of time, so you're being confident it is fully dry. When it comes to flame drying, admittedly, you can get it much hotter. The downside being that there is a risk that you overheat your glassware. So you need to be sure, especially with a flame drying with a Bunsen burner or a blowtorch, if you ever see orange spots, and that is when the sodium is escaping from the glass and you're getting it too hot. There's been various incidents I've seen and done myself where I've overheated the glass and you'll start to see it warp. And obviously, it's a bit more difficult to do it safely without burning yourself. So if you ever don't have the glassware ready, then doing a flame drying or using a heat gun is always an alternative that you can do. And of course, if you don't have access to a suitable oven, then it's still sufficient. So both are valid. One's safer than the other, and one's a bit more convenient also.
Thank you. Next question, when wouldn't you use liquid nitrogen in the trap?
That is a very good question. Personally, I've always used liquid nitrogen in the trap, especially the one on the line. And the reason why you want that on the line is because that's your fail safe. That's the last resort. So it means it will essentially try to catch everything. But if you want to use an external solvent trap, and you know you're removing something that has a boiling point of 40 degrees, then, or even a freezing point of minus 40 degrees, then you don't necessarily have to go to liquid nitrogen temperature. So a dry ice acetone bath should be sufficient. And you can obviously use that on your line as well. You just need to keep in mind, particularly if you're doing the freeze pump 4 method, that even a liquid that is frozen might have some volatility. So by using a liquid nitrogen trap, you obviously avoid the risk of that solvent going through to your pump, but you do increase the risk of liquid oxygen contamination. So that it's definitely something to consider. If you're first training people on a line, then you can use a dry ice acetone trap to begin with until you're confident that they have the skills and the experience to avoid making mistakes on the line.
Cool. Should the overpressure bubbler be closed tightly once hearing a popping sound from it, indicating pressure buildup? The problem is that after purging argon, they don't see any flow of argon. Could this be related to the direction of the stopcocks?
It's kind of so when it comes to the overpressure bubblers, you're right that you don't. The whole purpose is that you don't see constant bubbling. You can loosen it or tighten it if you want constant bubbling. So if you want to release pressure more easily in your line, but ideally it doesn't bubble unless you're generating gas. One way that I found of kind of helping myself know that gas was going through the line is to have a inlet oil bubbler. So when your inert gas first enters the Schlenk line, you can have a very small oil bubbler so you can see that gas is flowing. And that is also true that if you're ever opening a stopper, you'll see it increase. And once the pressure is built within your line, you'll see that bubbler stop. So that's one way to still get the benefit of being able to monitor the flow rate whilst not having a typical bubbler that is constantly bubbling. Hopefully that answers the question. It's a bit, I didn't fully understand it, but hopefully that does address kind of some of the dialing in that you have to do when you first get an overpressure bubbler.
Cool. What is the best practice when liquid dioxygen is observed in the cooling trap?
That is a good question. So one thing that is often recommended is that I say just leave it, and by that I mean that you avoid doing any further chemistry on your line. You close the sash so that if something does happen, everyone's protected. Because, well, first you want to stop the source of the leak if you know what it is, if it was an obvious one. Because the temperature of liquid oxygen and liquid nitrogen is similar, the liquid oxygen that is condensed will slowly evaporate over time. So even with the vacuum running. So that is probably the safest thing to do. The other things that you can do is kind of shut down the line and allow it to warm up and naturally evaporate. Obviously, make sure that the vent valve is open. Again, make sure that the fume hood sash is down so that you are protected. The main risk is when you have solvent that is collected in there as well. I would, as mentioned on the slide and also in the organometallics tutorial where I talk about safety considerations, the Safety Net website has a lot more information, and they have a standard operating procedure for when you do run into the risk of liquid oxygen condensation. So I definitely would consider consulting that as kind of better guidance than what I shared in the presentation, which was quite brief today.
Thank you. We have a few more questions. Which orientation of the cooling trap do you recommend? I've seen both directions in different labs.
This is something I still do not know, sadly. I've seen both. There's benefits for both, and there's what's the benefit for one is then flipped when you flip it the other way around. I personally like it, or yeah, my personal preference, I believe, is when um, the kind of inlet, the tube, um, comes from the line into the trap versus the other way around. But I've still, after all these years, have not found a consensus on this. It's definitely personal preference. You can either get, especially when it comes to the main reason that people ask is that it's to avoid the blockage when you're dealing with the easily freezable solvents, and it would either clog in the tube or around the tube. And I do admit that around the tube is a bit bigger, so less chance of blockage, but it's possible either way.
Cool. What is the perspective on using rubber septa and Syringe for cycling a common RB flask instead of typical Schlenk line flask?
Um, I'm against it, but I do know that for things that are less sensitive, then that is completely sufficient. Um, I am against using rubber septa for vacuum if you are just using a round bottom flask, because something is like semi-sensitive, then even purging the flask with inert gas is a safer alternative and will probably give you a similar result. So that's something to keep in mind. I would definitely prefer purging over evacuating a flask with a rubber septa, especially because you're then probably trying to evacuate it through a needle, and that is so small that it would take a long time to evacuate fully anyway, whereas purging, you can flush a lot of gas through it in a shorter period of time.
We have two final questions. So is it normal that the pump goes to 10 of the power of -3 millibar, while the manometer of the Schlenk line only detects 10 to the power of -2 millibar? Is it okay to lose an order of magnitude from the pump to the line?
Um, I've seen this before. It might suggest there's a small leak somewhere within your line. It will obviously be very small if you're still getting 1 times 10 to the -2 millibar on your line. Um, when I've witnessed this myself, I found that if your manometer can be directly connected to your line but isolated, as soon as you isolate it to stop it from getting constant dynamic vacuum, you'll see that pressure reading increase. So even the way that your manometer is connected to your line or the tap that isolates it could be the source of the leak. I wouldn't be concerned if you're still getting those vacuum pressures even 1 times 10 to the -2 millibar. But yeah, it still suggests that if there is a differentiation, there is a leak closer to whichever one is reading less or worse, let's say.
One security question. So what precaution to take while doing Schlenk line filtration under inert atmosphere?
So when it's just a cannula filtration, then I think the main precautions are just to ensure that stuff doesn't get clogged and that you do have a bubbler with a constant release. Some people, I've seen some people do this without the safety release of a bubbler. They just close the bubbler completely so that you have high inert gas pressures. Um, It should technically be safe if you have the bleed needles, but it's something I don't personally recommend. You can slightly shut off towards the bubbler, so you might have block-offs just before, and if you have a Teflon tap, you can partially close it to increase the pressure whilst still allowing the safety mechanism of a kind of a relief system if needed. Other things to keep in mind are that if you're depending on the chemistry that you're doing, the liquid or solid that you're filtering off or filtering to collect may be pyrophoric. So when you remove that from your flask, your filter is going to be covered in pyrophoric organolithium, so it might catch fire. So you need to have an appropriate quenching solution on hand to deal with that. So that would be the other main safety consideration that I have for cannula filtrations. The other type of filtrations that I weren't able to speak about today is the filtration through a filter stick or through sea light, which is detailed on the website and the guide, and they have similar safety precautions to what we've seen for some of the freeze pump for methods, for example.
There was one last comment or recommendations. Mr. Knebler Boost said that he would use 2 traps to create a U-shaped pathway to liquid transferred to the pump or back by the reagent by accident.
Yeah, that's definitely the ideal situation. And yeah, 2 traps that are close together that they can have a single dual liquid nitrogen is perfect if possible. That would be the ultimate solution, but it's definitely more of an advanced feature that most Schlenk lines wouldn't have. But yeah, that definitely solves the problem if you have both.
Cool. Thank you very much for the great webinar today. We saw a lot of questions. Thank you for taking the time to answer that. I hope everybody enjoyed the webinar. We will definitely send you the recording after the webinar with some links to the Schlenk Line survival guide, obviously a little bit of an advert to our great Vacuum Pure pump and the Vacuum Extended, just to enjoy it, better equip your Schlenk line. Thank you for everybody attending today. I hope you enjoyed the webinar. Thank you, Andre, for taking us through, and have a good afternoon, good start into the day. Bye-bye, and see you hopefully next time at one of our webinars.